Force and electric charge. So we'll start just by talking about electric charge. What is electric charge? Well, we don't really know what causes electric charge. But electric charge is a fundamental property of an object. We'll be talking mostly about point particles. And in the world, there are two varieties of charge, positive and negative. As I say, we don't know what causes it. All we know is how it behaves. And so we're going to start by talking about that. And our unit of charge is called the Coulomb, which we're going to specify with a capital C. So the smallest amount of charge that we're going to deal with is going to be the proton and the electron. And this charge is 1.6 times 10 to the negative 19th coulombs. And so these are the particles that make up atoms. And so the majority of things that we're going to talk about dealing with charge will be a result of these particles. The key to understanding how to solve different kinds of problems involving electric force is just this simple idea that like charges repel and opposite charges attract. And so just in the picture here, the positive charge is attracted to the negative charge, and the two negative charges repel each other. Now, one thing to note, due to Newton's third law, the two forces here, so the force that this positive charge feels of attraction and the force that the negative charge feels of attraction are equal and opposite. Our equation to calculate the electric force is called Coulombs Law, and it looks like this right here. And so this is the electric force on a point charge Q1. So you can draw a little picture. So maybe this is Q1 and this is Q2. So this equation gives us the force that Q1 feels caused by Q2. And the other key part of this equation is that R is the separation between these two particles, the distance between the 2 point charges. So the force is directed along the line joining the charges, and the way that it works is it's repulsive if it's the same sign charges and attractive if they have opposite sign charges. And so the way that I usually think about this is this equation is I make the force an absolute value here, and so we solve for this equation and then we draw arrows for vectors because force is a vector, all right, to figure out what direction the force might be in. So we'll do some examples to show you exactly how this works. Now, one thing to note here is there's a little constant in here, K. K is 8.99 times 10 to the negative 9. We usually just sort of approximate that as 9. It just works out that way. Now, a couple things here. So this works hopefully like we would think it would. First of all, the magnitude of the force drops off at larger distances. And so if they're separated by a really big amount R, the force will be relatively smaller than if they're closer together. Also, the larger the charges are, the bigger the force will be in general. And as we mentioned before, the magnitude of the force is the same on both charges due to Newton's third law. So it doesn't really matter which one you call Q1 or Q2 if you're trying to find the force on one of them. And this is the inverse square law, this 1 over r squared business here. And we've seen this before with gravity and also with sound. So here's an example question. So we have 4 charged spheres, capital Q, and then a little one that's a Q and a 2 times Q. And in which case is the force on charge capital Q the greatest? So pause here and think this one over and let me know what you think. Okay, so I get case A. And so we can kind of, first of all, just sort of argue this. So our equation, okay, our new equation we just learned is K Q1 Q2 over r squared. So what's happening here is in the second case, you're doubling the distance and doubling the charge. And so right away you might think, well, hey, those two cancel out. Well, the problem is that the distance is r squared. And so the distance has a larger effect than the upstairs part, the Q1 and the Q2. And so what we're doing here is we're increasing one of the charges, but since the distance goes as r squared, that's a more important effect. And so what that means is when I move them back 2D, even though it's twice the charge, case A will be larger. Now you can also just plug in some numbers to kind of show this to you. So if I take this equation and do it for case A, I get K big Q little q over my d squared. So that's for case A. So that would be the force in case A. And then if I do the same thing for my force in case B, I get K and I'll get capital Q 2 times little q. And then if I take 2d squared, I'll get 4 d squared, and so the 2 cancels with one of the 2's in the 4, and I'll end up getting 1/2 k big Q little q over d squared. So I get exactly half of what A was. And so A is, in fact, the greatest one. So it's good to be able to think about it conceptually, but it's also nice to be able to plug into the equation there. So the big question is, what do we do if there's more than one charge that can apply force to our point charge? Well, luckily, it works out. We can use what's called the law of superposition. And so all we have to do is just add the forces of all the different charges one by one, which is a really nice way to do it. Now, it can get tricky, but this is easier than other ways it could work out. So we have Coulombs Law, and so we got two charges here. So just in a real simple case, so again, like I was mentioning before, we use this equation to figure out the magnitude, the size of the force, and then what's usually easier is to draw arrows to figure out which way they're pointing. And so in the case here, on these two charges, the force is going to be inward. It's going to be attractive forces. Okay. Now, if there was another charge over here, for instance, okay, again, what I do is I can sort of connect these charges with some sort of invisible lines, and the force should be along those lines. And so the force that this red one applies on our Q2 is going to point up that way, and the force that it's going to apply on this Q1 is going to be that way, again, along these little dotted lines. And so basically by knowing how like charges and opposite charges work, we can always draw a vector that represents our force, and then along with our Coulombs law, we can go through and calculate what we need to calculate. One more question here. So three charged spheres are arranged as below. What direction will the electric force on charge A point? All right, so we got two positive charges, then point A there. So think about this one, pause, and then let us know what you got. All right, so for this one here, I get that the force is going down. And so let's look at this. And so if I look at these two charges, I know that, again, the force is going to be directed on the line that's connecting these guys. And so if I draw this positive and this negative, again, it's going to be a force of attraction for both of them, something kind of like this here. All right, and so this is the force from the charge. We want to call this one the force on the left. This is the one from the force on the right. And so force from the left, force from the right. Now, you can kind of see here what's going to happen is this force is going to have two parts. There's going to be a part going down from each one, and then a part going left and then going right. And so basically the left and right part of these two forces will exactly cancel because the charges are the same and the distances are the same, and the two parts going down are going to double up and make a really stronger force going down. So the direction of this force should be down. And finally, we're going to do an example here of the kind of thing you might do with Coulombs law. So here we have a setup where we're given three charges are together, as in this picture. We're given their three charges, the value of their charges, and the distance of their separations, the r distance is there. And then we're asked, what is the force on charge A? And so the forces are A, B, and C, and we want to find what the force on charge A is going to be. And so we're going to go through and do this here, set this up. So basically, using the idea of superposition, what we'll do is we'll go through and find each force separately. So the first thing is find the force due to charge B. And so this is charge B, this guy, acting on charge A. So we go to our Coulombs law, and again, I like to think about it as this is the absolute value. And so I just want to calculate a number, and then I'll set up what the vector is later once I think about it. And so the first part is just plugging in a bunch of numbers. We got the k value. I got the two charges, 5 times 10 to the negative 6th, 3 times 10 to the negative 6th. And then the distance of separation there is the 0.15 squared. So when I plug this into my calculator, I got almost exactly 6 newtons. So the question now, which I think is the hardest part, this first part is just plugging in numbers, is what's the direction? Well, it's B and A. These are both positive values, and so we know when they're both positive, it's going to be repulsion. So the force will be down. So this initial force of B on A is down 6 newtons. Now the second part is let's find the force due to charge C. Again, we use the same setup to do this, Coulombs law. We plug in our constant. Now we're using the values of 4 and 3. Now the thing is, the way I do this, and most people kind of think about this, is since I'm just getting kind of the magnitude of the force, I don't care about this negative 4. So I'm going to plug it in here as just 4 times 3, and then I'll think about what the direction of the vector is later. Okay, and so when you're doing the forces here, you can just sort of get rid of the negative signs, just find the number, and then figure out what the direction is later. And so when I plug this into my calculator, I get 1.72 newtons. And again, we want to know is what's the direction? Well, so this is charge C acting on A. These are opposite charges, and so they're going to be attractive. And so the force is going to go this way here. Now, most of the time with these kind of problems, you've sort of done the physics part, and now it comes out to be math. And so on my charge A, if we did this correctly, I got my force in the x direction is 1.72 newtons, and my force in the y direction is 5.99 newtons. And so to end this up, generally they'll want to have some sort of collection of these, maybe as the magnitude and the direction. Not all the time, but you'll oftentimes have to do this. And so the way to do this is we want to find the actual force, which kind of points that way. And so here we can set up just a vector diagram. So the y direction is 5.99. This is 1.72. So to find the hypotenuse of that, I just do this here and get that the total force is 6.23 newtons. And then I can also here solve for this angle by doing inverse tangent. Okay, so remember that tangent of theta is opposite over adjacent. And so if I, in order to find the angle, theta, I just take the inverse tangent of opposite over adjacent. And so here, if I'm finding this angle here, the opposite is 1.72, and the adjacent is 5.99. So I plug that in, and I get that my angle right there is about 16 degrees. And so that's our answer. Now, it's always good to kind of go back and look at your picture. And so if I go back and look at my picture originally from back over here, this sort of has a pretty good picture of this. So this force we know is going down. This force we know is going this way. And so the overall force will go this way here. And so we have sort of a, you always want to go back and kind of make sure it makes sense to you. All right.